I'd like to welcome Aidan Wouters.
Hey guys, for those of you I haven't met, my name is Aidan Wouters. I'm a graduate student at Carleton University working with Dr. Christina Davey and Dr. Jeff Dawson. And before I get started with my research today, that might help. Before I get started with my research today, I'd love to see a show of hands for who here has seen a bat flying out in the wild. Bat conference, that's what I hope to see. Okay, but who here has seen a bat walking out in the wild? Still a few, but not as many. Since they are the only mammal group capable of true flight, it makes sense that we would be interested in understanding how bats fly. But what if this focus on flight has led to a blind spot regarding how they interact with the ground? Oh, I think I'm on play. So my research actually started with another student's observation. Laura Scott here, as a master's student with Christina Davey, and Jeff Bowman conducted behavioral experiments on roost site selection in 2 species. And she captured this amazing footage of Myotis leibii, aka the very cute eastern small-footed bat. And this bat doesn't look like it's struggling to move on the ground. On the contrary, Myotis leibii looks surprisingly comfortable. And it's this observation of Laura's, as well as their tendency to roost on the ground, that inspired my own master's research, describing the kinematics of terrestrial locomotion in Myotis leibii. Because understanding how bats move on the ground, especially this species we still don't know too much about, might help us understand how they're interacting with their roosting and their dietary niches. I've used the term kinematics, but what does that mean? Kinematics is the study of the motion of a body without considering the forces or physical drivers behind it. So when we look at that, we look mostly at stride cycle and gait patterns, with strides being the motions that occur between a specific event and when that event reoccurs, such as from my left heel strike to the next time my left heel strikes the ground, that being 1 stride. A gait is when we see the same repeated patterns across several sequential strides. So what do we know about kinematics on the ground or terrestrial locomotion in bats in general? The answer is not enough, but thank you, Dan, for the things we do know. We've broken them down mostly into 3 categories. So we've broken them down into the good, the bad, and the ugly, with good bats being bats that are pretty comfortable on the ground, and they show these repeated stride patterns that are consistent enough to be considered a gait. We have our bag crawlers. These guys are not really able to do much on the ground other than hopping, flight-initiating jumps to get themselves the hell out of there. And then you have the ugly crawlers. These guys are able to kind of shuffle and push themselves across the ground, but they're not showing strides that are repeating or consistent enough to be considered a gait. So that is why I did my research, to look at these qualitative and quantitative kinematics in terrestrial bats. So, well, hopefully, possibly terrestrial bats. So when I say qualitative characteristics, I'm looking at things like the points of contact of limbs with the ground or their overall posture. And when I look at quantitative kinematics, that's things like distances and speeds that they're traveling at. So how did we do this? We put bats on treadmills, and we used an external motor capable of going up to 37.88 centimeters per second. We did samples with both the treadmill off to see their natural gaits, as well as moving them to lower and higher velocities. We filmed these with high-speed cameras that went and captured 227 frames per second, and we had 2 overlapping oblique views from one side, a straight-on view from the opposite side, and a camera oriented over the treadmill facing down. Because we did this all with infrared lights, we were able to do it in the dark and directly out in the field. We built all of our equipment to be fully portable, not fast, but portable. And so we set it up and took it down each night. This meant that we were able to capture individuals during surveys, run them in the experiments, and then release them without taking any out of the field. This meant we minimized our overall handling time. So after we collected all of this data, and there is a lot, we had to digitize it. So I used a software called Tracker, and I manually tracked specific points throughout each frame of my footage. Today, we're just going to look at the 4 feet, and for the sake of time in this presentation and the amount of data I am swimming through right now, We're just looking at one of my Myotis leibii. So you can see here that we've got this figure. The colors on the figure correspond to specific limbs, and these are the same colors you see in the tracker footage below. The period between the two lines is one stride cycle from the left forelimb strike to the next left forelimb strike, with these filled in color blocks, meaning that limb is in contact with the ground. Where the blocks are blank, that means that limb is in motion through the air. So this bat covered 8.51 centimeters over this span, but it actually covered 5.22 centimeters of that in a single stride alone. And it completed that stride in 0.22 seconds. This gives us our stride frequency, with our stride frequency being how many strides they're able to complete in a second. That's 3.03 strides. What does that actually look like in real time? Pretty fast, so 21.19 centimeters per second, aka 0.76 kilometers an hour, for a bat that's only about 8 centimeters long on the longer side. It also did this always keeping one foot in contact with the ground, which means this is a walking gait. So now we're looking at our bat's top speed. So this figure shows the exact same time period as our natural gait sample from before, but it increased its total distance traveled to 13.69 centimeters. It increased this distance by increasing its stride length. So it actually increased how far it was able to travel in one stride up to 7.6 centimeters. It decreased the overall time required to complete a stride, which allowed it to almost double its stride frequency from 3.03 strides per second at its natural gait to 5.63 strides per second at its max speed. But how did this actually affect their max speed? It almost doubled it. So this bat is going 37.88 centimeters per second, which you might remember is the maximum speed of our treadmill here. So this might not actually be the fastest our Myotis leibii is capable of going, and this is not the only bat in our sample size that maxed out our treadmill. So this corresponds to a rate of 1.36 kilometers an hour, but it still always has at least one limb in contact with the ground and is therefore still a walking gait. So how do they compare to other good crawlers? Well, we've got our famous common vampire bat, and they both have similar foot strike patterns that we're seeing with these diagonal pairs of limbs, so like the right forelimb and the left hind limb, supporting the body while the opposing diagonal pair moves forward in space. But their body alignment is slightly different. Vampire bat has a little bit of a curve to it as it moves, but overall its nose, pectoral girdle, pelvic girdle, and tail is pretty straight, and it's rotating its hind limbs underneath of its body to go forward. In contrast, Myotis leibii has a pretty noticeable hip swivel to it, which is really helpful considering it's not rotating its feet under its body. It is swinging its hips side to side to bring those limbs up around these sides, kind of like a lizard. And they're also a little different in this sense. The vampire bats are sitting really high off the ground with their torso when they move, which helps with the underneath rotation of the limbs. Myotis leibii can't get its feet underneath that. So they're actually really low to the ground here. And you'll notice that not only is it low to the ground, but it gets lower the faster it goes. So on the top is our natural gait, and on the bottom is our max speed. Should it surprise us that Myotis leibii are good on the ground? Maybe not. These guys not only have non-volant prey often found in their fecal samples, but they also have a really noted tendency to roost in rocky ground environments like talus slopes. So maybe it makes sense, maybe it's even advantageous for them to be good and comfortable on the ground. But this makes them a really good example of why we should examine why and how more bats move on the ground, because they might not be the only species with some surprises in store. Which is why this isn't the only species I included in my research. I actually sampled 3 other bat species, so stay tuned for next year for roosters versus non-ground roosters. Thank you very much, and special thank you to the bat team. Not only will I not have bats to run without you, but you cannot run this treadmill by yourself.
Oh, it's on now. Okay. Thanks. Does anyone have any questions? That was really interesting.
Do you know what the top speed is for the vampire bats and how the sort of the differences in the way they move can affect their speed?
So the vampire bats actually have two different types of gaits. They have walking and running gaits. So Riskin, your treadmill maxed out at 1.15 meters per second, I think.
I want to say 2.5, but it's been a long time. I haven't looked at that graph in a long time.
Anyways, so his vampire bats were running anywhere between 0.56 meters per second, and the last time I looked was 1.15 meters per second. So we didn't reach that speed with our treadmill. We did an external motor, partially because it was easier to get like a consistent speed going, and because it was much quieter than the drills we had available, which is the method they used, and we figured the quieter might make the bats a bit more behaviorally nice.
I think that's all the time we have, actually. Sorry.
It's all good.
Thanks.